Richard James Mathematics Resources will now present Grade 4 Practice Paper 4, Part D. These videos will take us from number 37 all the way to number 49, which will take us to the end of Grade 4 Practice Paper 4. So we will begin with problem number 37. Which two shapes make up this diagram, Jerry? What two shapes do you notice there?
A rectangle and a triangle.
Okay, so you heard that. A rectangle and a triangle. And that is represented by which option?
Option C.
Okay. The figure on the right is a triangle. How do you know a triangle?
It has 3 sides.
Okay, first of all, it has 3 sides. So we can count the 3 sides. As long as it has 3 sides, it is a triangle. So we are just making sure that we highlight triangle in all of the options. Any figure that has 3 sides is a
Triangle.
okay, triangle. The figure to the left has how many sides?
4.
4 sides. And as a matter of fact, what is that shape?
A rectangle.
A rectangle. Now, if an object has or shape has 4 sides, that does not make it a rectangle. But we will take a look at the special features of a rectangle so that we just do not say a rectangle and a triangle. Option C is correct, and then we just move merrily along. And students will take a look, some students will take a look at any 4-sided figure and call it a rectangle. So it has 4 sides. It is a quadrilateral. What does quadrilateral mean?
4 sides.
Right. So quadrilateral means 4-sided figure. Lateral as in line and quadri as in 4. So it is a shape that is made up of 4 lines or 4 sides. A square is a rectangle, but let us take a look at the previous statement. It is a quadrilateral. A quadrilateral is a 4-sided figure. The quadrilaterals in the option are rectangle and square. So the quadrilateral that we have mentioned in the option are rectangle and square. And we will find square in option A and option B. And of course, we have highlighted all of the occurrences of rectangle. A square is a rectangle, but a rectangle is not necessarily a square. The figure on the left is more certain to be a rectangle than a square. The option that has a red and a blue is correct. And the red is for?
Rectangle.
And the blue is for?
Triangle.
Right, so the option that has a red and a blue, which is option?
C.
Right, and that one is our correct answer. A square is a quadrilateral with all sides equal and all angles equal. And all angles are equal to 90 degrees. So in our square, all sides are equal and all angles are equal. All angles are therefore equal to 90 degrees. In this particular case, the figure is obviously not a square because the sides are not equal. All sides are not equal, therefore it is not a square. In a precise diagram of a polygon, all of the equal sides are marked with the same number of strokes. I hope that Jerry is paying attention. Or dashes, to declare explicitly that they are equal. So, in a precise diagram of a polygon, all sides are marked with the same number of dashes or strokes. And that will tell us that all of the sides are equal. But are all of the sides equal in this particular case, Jerry?
No.
Okay. Can you tell me which two sides are equal?
The left and the right.
The left and the right. So we have these two sides are equal. And which other two sides are equal?
The top and the bottom.
Alright, so we have also that these two sides are equal. But we have each one of these sides marked with a single dash. So we are saying at this instant that they are equal, but they are not. Therefore, the sides that are equal should have the same number of dashes or strokes. According to the dashes that we have there, it would mean that the quadrilateral is a square, because each side is marked with a single dash, saying that all of them are equal. According to what we have there, the quadrilateral should really be a square. Each side has a single dash, which tells us that they are all equal. But are they equal, Jerry?
No.
They are not all equal. Since the quadrilateral is not a square, but a rectangle, only opposite sides of a rectangle are equal. So opposite sides should have the same number of dashes. So we are fixing the problem. The left side and the right side, they have how many dashes?
2.
That means that they are equal in length. And the top and the bottom, they have how many dashes?
1.
Right, so they are also equal in length. So for a rectangle, opposite sides are equal in length, and all of the vertices, all of the angles are equal to 90 degrees. Although it is not the case here, sometimes it is difficult to tell if a figure is a square without measuring it, because a square is a rectangle. If we say that the figure is a rectangle, we are sure to be correct. Now, if we have a diagram, and the diagram seems as if all of the sides are equal, it is very difficult for you to look and tell. Maybe it is difficult for you to tell. So you are tempted to say that it is a square because all of the sides appear to be equal. But because a square is also a rectangle, if you call the object a rectangle, then you would still be right, even if it is a square. So if you call it a rectangle, you will still be correct. But if it is obvious that sides are not equal, then we are sure that we cannot call it a square. So unless all sides are equal, and we are sure that all sides are equal, then we cannot say that it is a square. And that is why in a diagram, and the mathematicians will tell you sometimes in the solution of a problem that the figure is not drawn to scale. But whether or not it is drawn to scale, we have other indications in the diagram that can tell us whether or not it is a square. For example, how the sides are marked. So if the sides are all marked with a single dash, then we know that it is a square, even if by looking it just looks like a normal rectangle that is not a square. As long as the examiners or those who are setting the examination give you the problem with each side having a single dash, they intend that you interpret the diagram as a square. If not, then we have to say that it is a rectangle. But if we say it is a rectangle and it is really a square, we are not incorrect. If a figure looks like a square, but we are not sure of the measurements of the side, then we may say that it is a rectangle to be on the safe side, because a square is a
Rectangle.
Is a rectangle necessarily a square?
No.
Okay. Which shows an angle that is greater than a right angle? Which one is a right angle, Jerry?
Option C.
Right. Now, if we say an angle that is greater than a right angle, then we are required to understand what a right angle is like. So we should know what a right angle looks like. But the examiners, they have made life easy for us by also including a right angle in one of the options. And Jerry said that the right angle is in option C. So first of all, there's a right angle among the options. Where is that right angle? Right at option C. There it is. A right angle is equal to
90 degrees.
90 degrees. It is a quarter of an entire revolution, and it is the one that is marked with straight lines instead of a curve. So this is your right angle. We have straight lines marking that angle like that, and then other angles are marked with curves like that. The right angle is this one that is marked with straight lines. Greater than a right angle. We need the one that is greater than a right angle. Which of those angles is greater than the one that we have in option C? Which one is greater, or obviously greater, or appears to be greater, Jerry?
Option D.
Okay, option D is greater. Therefore, option D is our correct answer. The angle is in reference to the open space between the two line segments. The angle is in reference to the open space between the two line segments. So we have the two line segments, and we have them opened or giving a span like what we have right here, and we'll take a closer look at what we mean. Which span is greater than the one in option C? Notice that this is just like that, and this one is all the way around here. So option D is the correct one. The one with the greater opening is option D. So that one is our correct answer. We may think of an angle as two line segments clasped together, then opened, like we will see in the diagram. So there we have, it just appears to be one because they are close together, they are clasped together. But we have how many line segments there, Jerry?
2.
Right, but they are clasped together, so it appears as if we only have one. So let us open like that. Right, so that is your right angle. And that angle is also equal to 90 degrees. The line segments are opened to a right angle. Which one in the option has a greater opening than the one that we have there? The one with a greater opening is option D. Students are expected to be able to identify a right angle at sight. We are also expected to be able to judge just by looking whether an angle is greater or smaller than a right angle. So we are required to just look and tell if that is a right angle or closely approximated to one. And we also need to be able to look and see which angle may be greater than or smaller than a right angle. Students are not to be deceived by the length of the lines that are used to form the angle. Because some students may think that the longer the line, the larger the angle. But the length of the line does not tell us the size of the angle. It is the opening, how wide the opening is, that tells us the opening as the line will open like that. It is the opening that tells us how large an angle is. In which diagram is the dotted line a line of symmetry? In which diagram is the dotted line a line of symmetry? What do we mean by a line of symmetry? We will see what we mean by a line of symmetry in a short while. The dotted line, a line of symmetry. A line of symmetry is one which divides an object into halves that are mirror images of each other. So that line divides. If it is a line of symmetry, it will divide the object into halves that are mirror images of each other. Jerry, does that line divide the heart into halves?
Yes.
Okay. Are those halves mirror images of each other?
Yes.
Okay. But later on, we'll take a look at what we mean by mirror images. If one half of an object is reflected in its line of symmetry, then the other half will be obtained in such a way that we will get the entire object. So if we have half of the object and it is reflected in its line of symmetry, then we will get the other half of the object, and we will also take a look at what that means. If an object is reflected in a mirror line, it is as if it's flipped over or inverted. Inversion does not mean that it is upside down. Inversion may mean quite a few different things. For example, that it is turned around the opposite way. And that is the kind of inversion that we get when we reflect an object in a mirror line. So, let us take a look at that. In mathematics, something that is flipped over sideways is also inverted. We say that it is laterally inverted. So if we have a page of a book and we turn the page, that is what we call lateral inversion. So if we have it on one side and we just flip it over, now it is laterally inverted. And that is the same effect that a mirror line has on an object. Not only that, but the mirror line can act as a line of symmetry by reflecting each half of an object in order that the entire object will be formed. So, okay. So what did you notice, Jerry? Do you see half generated on the right hand side?
Yes.
And half generated on the left hand side?
Yes.
And the two of them together, does that form the entire object?
Yes.
Right. Because sometimes we have, for example, in this particular case, if we take, for example, that we are using this line to divide the heart in this way. If we flip this part over here, will we get the other half?
No.
Right, so the entire object will not be generated. So we will have cases in which the entire object is not generated if we use the dividing line that we have there as a mirror line or our intended line of symmetry. So we take half of it. If half of the object can be used to generate two halves that are mirror images of each other, then we are sure that the line is a line of symmetry. So we use this line as our mirror line, and we take half of the heart, and it is generated on this side. We flip it to the other side, and the entire object is generated. So we are sure that the line that we have here is a line of symmetry. Notice that when one side of the heart is flipped over, the other side is formed. That is the effect that a mirror line should have on an object, and the line of symmetry on each side of an object. So the mirror line will have the same effect on an object, and the line of symmetry will have the same effect on the object. So the line of symmetry is actually a mirror line that reflects one half of the object and the other half is generated. A line of symmetry is one which divides an object into halves that are mirror images of each other. So first of all, if the object is not divided into halves, then the line is not a mirror line. If one half of an object is reflected in its line of symmetry, then the other half will be obtained in such a way that we will get the entire object. Maybe we will do that again. Right. A line of symmetry is therefore like a mirror with one half of the figure, whichever one being the object which is reflected, to give the other half which is the image. So a line of symmetry is therefore like a mirror line with one half of the figure, and it does not matter which one, being the object which is reflected, to give the other half which is the image. If we have one half and the mirror line, when we reflect that half, the other half will be generated and the entire object will be the result, as we have it right there. If we reflect the triangle that we have in the mirror line, we say that the original triangle is laterally inverted. It is flipped over or turned around sideways, but not just sideways, but the opposite way. So it is flipped over the opposite way. So the mirror line will act like our center, like the middle of a book, and we just flip it over like a page. So when we flip the page over, it is now a lateral inversion of what it was before. The triangle and its image will form an object that is symmetrical about the mirror line. So if we put the original triangle in, then as long as we reflected the triangle in the mirror line, then the entire thing, or the object that is formed by the triangle and its image, that object that is formed by the triangle and its image is symmetrical about the mirror line, and the mirror line therefore acts as a line of symmetry. The mirror line is therefore called a line of symmetry. Students are required to be visually familiar with an object and its image relative to a mirror line. As such, they should be able to tell if an object is symmetrical about a particular line. If an object is symmetrical about a particular line, then that line is called a line of symmetry. And what does symmetrical mean? It means that on either side we have half. And each half is a mirror image of the other. The first thing to identify about a line of symmetry is that it divides the object into halves. If the two sections cannot be identified as halves, then the dividing line cannot be identified as a line of symmetry. What is the first thing that we know about a mirror line? It needs to divide the object into halves, right? And what do we know that halves are? Just two parts? Two parts? No, two parts? Right. So that's the first thing. It has to divide the object into halves. And the halves have to be equal. Right, they have to be equal. Halves are not just any two sections of an object. Halves must be equal. Must be two equal parts. Which option has the dotted line dividing it into halves? Do we have any other option?
No.
Right. Option C is the only option that has the object obviously divided into halves. Only option C has the dotted line dividing the heart into halves. Using the mirror line as a dividing line, let us take one side of option C, flip it around and see what happens. So we are going to take half of option C and we're going to do the same thing and see what happens. Alright. When one half is flipped over or laterally inverted, the other half is generated, resulting in the entire heart being formed. There it is. If 6, what we usually say when we have something missing from the expression? Dash. But in this case, it is a box. We'll say dash still. If 6 dash, all of 2 plus 3 is equal to 1 is true, which sign must be where the dash is? Or we're going to say square. If 6 square 2 plus 3, and it is better to say all of. If 6 square all of 2 plus 3 is equal to 1 is true, which sign must be where the square is or the box is? What sign? Now, what we can do first of all is write the expression in a simpler form, and then the answer will be more obvious. For example, anything can be made simpler, Jerry?
2.
What can be made simpler, Jerry? What is there that can be made simpler?
2 plus 3.
Right, the 2 plus 3. And the 2 plus 3, what's that equal to?
5.
Right. So we may make that simpler. So let's go. In mathematics, operations in brackets are among the first to be carried out. Enclosed, we have 2 plus 3. Right, so operations in brackets, they take precedence over most other operation. And because those are enclosed in the brackets, then we may perform that operation first. So let us do that. 2 plus 3, and that is equal to?
5.
Therefore, where we have the 2 plus 3 in the brackets, we may replace that with 5. What else may we do? What else?
Cancel the brackets.
Right, we may cancel the brackets or leave them out. Right, so we cancel the brackets or leave them out. We just have that single operation or that single number inside the brackets, so we may just leave those brackets out. Also, because there is only a single operand, we do not need to enclose it in brackets. So we may do away with the brackets. And what do we just have there? 6,
Box.
5 is equal to 1. What will be in that box?
Subtraction sign.
Okay, right. So of course, this one, at this stage, now that we have simplified the expression to just that alone, we should not have any difficulty in determining what operation we need to put inside of that box in order that we are correct. And Jerry stated just now that we should put a subtraction sign there. So if we say 6 minus 5, that is equal to 1, and we will be correct. Which operator needs to go where the purple dot is in order that the result may be equal to 1? Divide?
No.
We should not divide. Although 5 goes into 6 only one time, there is a remainder of 1. Division is therefore not correct. So division cannot be correct. What about multiplication?
No.
6 5s?
30.
Right. 6 times 5, that result will be 30. The multiplication sign is not the correct answer. So we cannot multiply right there. Because 6 5s are equal to 30, we are sure that that's not correct. And if there is any operation that is left, then we know 6 plus 5, that's equal to 11. Addition is also incorrect. By elimination or by direct calculation, 6 minus 5 is equal to?
6 minus 5 is equal to 1.
So option C is therefore correct. A netball court has a rectangular area. Which of these shapes would look like a netball court?
B.
B is the correct answer. It is a rectangle, and we will take a look at what makes it a rectangle. Which of these is a rectangle? So there we have a rectangle. A rectangle has opposite sides that are equal, and opposite sides are also parallel. By now, we should identify the answer. It has opposite sides that are equal and opposite sides that are parallel. Additionally, there are right angles at all of the vertices. So all of the vertices of a rectangle have right angles. The illustrative rectangle was made in order that it might be a very close match to the one that we have in the option. So we have our illustrative rectangle right here. It was designed to be a close match to the one that we have in the option. And our illustrative rectangle is there, showing that a rectangle has opposite sides that are equal. These opposite sides are equal also, and that all vertices are right angles. There we have a near perfect match. The one that was constructed on principle matches with the one in the option. The correct answer is therefore option B. A square is also a rectangle. All of the features are the same, but additionally, all sides of a square are equal. So a square is similar to a rectangle, As a matter of fact, a square is a rectangle with all sides equal, but a rectangle is not necessarily a square. The table shows the favorite sports of some boys. Which two sports are liked by the same number of children? Which two sports are liked by the same number of children?
Football and basketball.
Football and basketball, and that is represented by which option?
Option B.
Option B. Now we can see, even if we do not count them, we can see that these are the same number. But as soon as you glance at it, if you understand the principles of a tally chart, then it is very easy for you to just look at this and tell that this is 17, this is 12, this is 6. So that's very easy for us to tell just by looking. When tallying data, the diagonal stroke is also counted. Each group that looks like this represents 5. When counting items that are tallied, count by 5 for each group of 5 and then add the extras. So we can just look and we see 5, 10, 15 plus 2, that's 17. Or we may say 5 plus 1, 6. 10 plus 2, 12. And of course, it's easy to see 3, 5, 16 and 2, 17. And this one is just 5 plus 1. That's 6. And the other one is also 15 plus 2. It's not difficult to see that's 15. 5, 10, 15. The sports that has the same number of children are basketball and football, and represented by option B. Represented by option B. If items in a tally table are organized in the way that they should, then the ones with equal number must have rows of equal length. If the items in a tally table are organized in the way that they should, then the ones with equal number must have rows of equal length. So let us take a look at the length of the rows. Which two rows are equal in length?
Football and basketball.
So there you have your answers, and you can have your answer without counting. There we have the lines of equal length. The ones with equal length rows are football and basketball. They are liked by the same number of children. As a matter of fact, we do not need to know the number of each in order to know that they have equal number. And we have shown how we might be able to do that as long as the information in the tally table is organized in the way that it should. In this problem, we need to determine how many children like track and field. We have it right here. How many children like track and field?
12.
Well, it is obvious right there. In this problem, we need to determine how many children like track and field. No sweat. The numbers were determined from the previous slide, so we have it right there. There are 12 of them, and this is represented by option C. The fact that the number related to track and field was asked for after the sports liked by the same number of children tells us that we did not need the numbers in order to tell those liked by the same number of children. This justifies the second method of solving the problem, in which we use the length of the rows to come to our conclusion. So notice that the number problem was given after the one that asked for the one that was liked by the same number of children, because we did not need numbers in order to tell which one was liked by the same number of children, because as long as the rows are organized in the way that they should, the ones liked by the same number of children should have the same length rows, and we would not need to count the numbers there. Then later on, we were asked how many children like track and field. A bag has 3 red, 4 blue, 5 yellow, and 6 black balls. If one ball is taken out, which color is it least likely to be? A bag has 3 red, 4 blue, 5 yellow, and 6 black balls. If one ball is taken out, which color is it least likely to be? Least likely to be. Place the balls in the empty bag in their respective numbers. So let's go. Place them in the empty bag. Now it is not empty anymore. In their respective numbers. They are all inside there now. It might be very plain that if you pick up a ball, a red ball has the least chance of being selected. Why is this so? A red ball has the least chance of being selected. Why is this so? Why is it that a red ball will have the least chance of being selected?
There's only 3 red balls.
And Jerry is saying that there are only 3 of them. We only have 3 of them. The fact is, the red represents the smallest number of balls that we have there in their types or in their colors. Because it has the smallest number, the one of which there is the smallest number has the least chance or is the least likely to be selected. Option A is correct. It might be obvious which has the greatest or least chance of being selected, but our colors may cause optical illusion by brightness or dullness. It is therefore better to count them in order to be on the safe side. So if we have all of those balls nicely mixed up inside the bag, take a look at the bag and you can see, maybe it is obvious to you that a black one has the greatest chance of being selected. And maybe it is obvious that the red has the least chance of being selected. However, in fear that we might have an optical illusion, because if some of the colors are bright or some of the colors are dull, we might have an optical illusion in which the brighter colors might appear to be more or greater because they are more obvious, and the duller one appear to be least likely or less likely because they are dull, so they appear to be smaller in number. So it is important that we make sure that we know the number of each, and the number is given to us in the statement of the problem, so we are sure that the one with the least number is the one that is the least likely of being selected. The graph shows the number of different types of cars in a parking lot. How many of the cars were Toyotas? How many of the cars were Toyotas? And Jerry is saying that 5 of them were Toyotas. How do we know the number of items? How do we know the number of items?
There's a graph.
Right. And Jerry is saying that because there's a graph there that says the number of cars. Well, the graph says number of cars, but the graph says other things.
Types of cars.
Right. So we will use the section of the graph, or this axis that we have here, a vertical axis that says number of cars. So we are sure that the number of cars are here. Therefore, the height of the bar is to be measured against this axis, which says number of cars. The number of items are determined in relation to the vertical axis. The height of the bars will therefore tell us the number of each item. Let us see how we might do this. So there we have rays going from the top of each bar going towards the vertical axis that contains the number of cars. So the number of each car may be determined by measuring the height of the bar against the vertical axis. And we know that that vertical axis is in reference to number of cars. Honda 2, Nissan 10, and Suzuki 3. The problem requires the number of Toyotas, which is 5. Option C is therefore correct. See, the height of the bar goes all the way to here. It is halfway between 4 and 6. And what is the number that you will find halfway between 4 and 6, Jerry?
5.
Okay, so we are sure that the number of Toyotas is 5. The graph shows the number of different types of cars in a parking lot. How many more Nissans were there than Suzukis? How many more Nissans were there than Suzukis?
10.
Well, Jerry is saying it's 10, but Jerry is just looking at the number of Nissans. Let me ask the question again. How many more Nissans were there than Suzukis?
7.
What's that?
7.
That's correct. 7 is correct. More. We will begin by finding the number of each item involved. Remember that the number is in reference to the vertical axis. The height of the bar will tell us the number of each. The height of the bar will tell us. So we have Nissan is 10 and Suzuki is 3. How many more? In order to find how many more Nissans there are than Suzukis, we may subtract 3 from 10. We are actually finding by how much 10 is greater than 3. By how much 10 is
Greater than 3.
greater than 3. Subtract, and the result is
7.
7. 10 minus 3 is equal to 7. The correct answer is therefore option
B.
B. The graph shows the number of different types of cars in a parking lot. How many more Nissans were there than Suzukis? It's the same problem. Take note of the heights of the bars that we are working with, but do not write down the number associated with each one. So we do not write down the number. Take note of the height of the bars. What do you notice? To find out how many more Nissans than Suzukis, we may count from the height of the bar for Suzuki to the height of the bar for Nissan. So what we do, instead of say 10 minus 3 as we did, and please do not tell me that we know the answer already. I'm just demonstrating another method that we may use to solve the problem. So we have right here, we are not going to say what we have there. And although it is obviously 10 here, that's not our concern. The method that we are about to use does not matter what the numbers are like. Not as yet. The scale of the graph goes up by 2 each time, and we need to consider the intermediate values, which will cause us to count by 1. So we are seeing that it goes up by 2 each time. Right? It goes up by 2 each time. What do we need? We will begin counting at the height of Suzuki, which will be our 0 mark. Where Suzuki is will be our 0 mark. So 0 will go right there, and we'll count up. Here goes. 1, 2, 3, 4, 5, 6, 7. Well, let's do it again. 0 is where we begin, and we step 1, 2. In this particular case, we are not going from this mark to the other, but we are also including the intermediate steps. So we have 0, 1, 2, 3, 4, 5, 6, 7. Jerry is saying it's 7. Well, we said that before. The correct answer is option B. Look at the circle in which lines have been drawn to show equal parts. So we are taking a look at the circle in which lines have been drawn to show equal parts. Shade 2 of the parts. So we are about to shade 2 of the parts. Shade them. Shade 2 of the parts. Right. Write a fraction which names the shaded parts. Write a fraction which names the shaded parts. Write a fraction which names the shaded parts. Draw other lines to divide the shape into 8. So what we will do first is write a fraction which names the shaded parts. So for our fraction, we have the fraction bar, we also have the numerator, and we have the denominator. What will be the denominator in this particular case, Jerry?
2, 4.
And what will be the numerator?
2.
Right. The denominator tells us how many equal parts the whole is divided into. And the whole is divided into how many equal parts, Jerry?
4.
Right, so the whole is divided into 4 equal parts. And the numerator tells us the number of those equal parts that are involved. As in this case, the number of equal parts that are shaded. So the numerator will tell us the number of equal parts that we are talking about. And we are talking about those two shaded parts. And that will therefore be our numerator. Draw other lines to divide the shape into eighths. So draw other lines to divide the shape into eighths. There we have it. What do we mean by eighths? Jerry, what do we?
Equal parts.
Alright. So eighths are those parts of an object that is divided into 8 equal parts. So we have the entire figure divided into 8 equal parts, hence we have it divided into eighths. Dividing into eighths means that the whole is divided into 8 equal parts, as an eighth is one of the equal parts of a whole. So an eighth is one of the equal parts of the whole. So if we are dividing it into 8 equal parts, or divided into eighths, then we need to divide the object into 8 equal parts, like we have right there. "5 years ago, Bob was 5 years old. Today, he is 2 times Pam's age. How old is Pam?" The first part of the problem requires that we find Bob's present age. And Jerry is saying that his present age is 10. Okay, that's correct. Let us see how we can show that his present age is 10. 5 years ago, not only Bob, but everyone was 5 years younger. The number which represented Bob's age must be smaller than his present age by 5 years. So we have 5 years ago and we have present age. Then we have that intermediate 5 right there. That 5 tells us that he was younger by 5 years. 5 years ago. What about his age 5 years ago? What was his age given as 5 years ago? He was 5 years old. So let us write down his age 5 years ago. So the first 5 is in reference to 5 years ago. The 5 that we have there is that 5 years ago he was 5 years old. His present age must be greater than his age 5 years ago, and it must also be greater than the number of years that passed. His age must therefore be the sum of his past age and the number of years that passed. So we have the age 5 years ago, and the number of years is 5. So 5 years ago he was 5 years old. So we need to add those two 5s. I wish that the problem had different numbers instead of 2 equal numbers. That would make the solution of the problem plainer. So it is obvious that there we have Bob's present age. His age is 10 years. Consider his age 5 years ago. We are taking a look at it from another perspective. 5 years ago, he was 5. For each year since then, we may add 1 to his age. Do not forget that it is 5 years ago that he was 5 years old. So 5 years ago, he was 5 years old. So for each year since then, we may add 1 to his age. It is now 5 years since. So that is his age 5 years ago. So to come up to the present year, we will add 1 year to his age for each year. And we know that there are 5 of them. We may therefore add 1 to his age for each of the 5 years that passed. So let us keep on doing that. Number of years, we add 1, then we add another 1, and we do that 5 times. And after doing it 5 times, we get his present age to be 10 years old. Now we will take a final approach in showing that his age is actually 10 years old. So let us place his age and the number of years that passed on a timeline. Present age that we do not know as yet. And we put that on a timeline. Past, present, and future. Let us go back in time 5 years. So from the present, we are going back how many years?
5.
5. Take note of his age 5 years ago. Coincidentally, he was 5 years old. So for 5 years ago, we need to have his age, which is 5 years old. Add a year to his age until we get to the present. So that's his age 5 years ago. We need to bring that up to the present age. And we therefore need to add 1 year 5 times. So that is his age 5 years ago. So we will step 5 times up to the present age, or to the present stage. So 5, and we are right here. This is his present age. This shows that his present age is 10 years old. This shows that he is presently 10 years old. Today he is 2 times Pam's age. He is 2 times Pam's age. So Bob is 10 years old, Jerry, and he is 2 times Pam's age. What is Pam's age?
Pam's age is 6. 10.
10 is 2 times Pam's age. So what is Pam's age? He is 10 years old.
Right.
And this is 2 times Pam's age. What is Pam's age?
5.
Right. So Pam's age is 5 years old. There we have the 10 years of Bob's life. Let us say that Pam is P years old. Bob is 2 times Pam's age. Times means that we multiply. In order to get Bob's age, we multiply Pam's age by 2, because Bob is 2 times Pam's age. How old is Pam? Now we have the equation which says 2 times something gives 10. What is it that we multiply by 2 and the result is 10?
5.
Right. So if we do not arrive at the result immediately, the answer lies in our 2 times table. what number do we multiply by? 2. And the result is 10. Because P is a number that we are multiplying by 2 and the result is 10. 2 times what gives 10?
5.
Right, so 5 is actually Pam's age. Pam is actually 5 years old. So 2 times 5 is equal to 10. 5 is the number that we multiply by 2 and the result is 10. It therefore means that Pam is 5 years old. We may treat the expression as an equation that we will solve algebraically. So we may just treat it like an equation. We multiply two numbers and the result is 10. How do we find the other? We need to find P. It is accompanied by 2 on the left hand side by multiplication. In order to eliminate the one that we are multiplying by, which is 2, we need to do the opposite of multiplication, which is
Division.
Eliminate 2 on the left hand side by dividing by 2. If we are solving an equation, and no doubt that we are using our common sense also, because we took a common sense approach to the solution of the problem, in which we are just saying if we multiply something by 2 and the result is 10, then that something has to be 5, knowing our multiplication table. Also, what is the operation that we carried out with the 10 and the 2 that resulted in the 5? So eliminate 2 on the left hand side by dividing by 2. In order to keep the equation balanced, because it is an equation, what is on the left hand side must be the same thing on the right hand side all of the time. Therefore, in order to keep the equation balanced, whatever we do to one side, we need to do it to the other side. So we will divide by 2 on the right hand side also. Divide by 2 on the left hand side? Cannot do that unless we are prepared to do the same on the right hand side. The 2 will be eliminated from the left hand side, and on the right hand side 10 divided by 2 is equal
5.
to 5, right? 2 is eliminated from the left hand side, and on the right hand side 10 divided by 2 is equal to 5. Pam is therefore 5 years old. On the diagram, draw 3 straight paths. One straight path from the clown to the rose. Straight path from the clown to the rose. One straight path from the rose to the dog. And what else? One straight path from the dog to the clown. What shape did the straight paths make?
A triangle.
How do we know that it is a triangle?
Because it has 3 sides.
It has 3 sides. A triangle is a polygon that has 3 sides. And cannot be a polygon unless the sides are straight, and they are, according to the statement of the problem, 3 straight paths. And if that was not enough, one straight path, so and so, another straight path, and another straight path. So we are sure that it is a triangle, because throughout the entire statement of the problem, the word straight is there over and over again. And the question is asked, what shape did the straight paths make. So we are sure that it is a polygon because of those straight paths. The shape is formed by 3 straight lines. A 3-sided figure is a
triangle.
The shape is therefore a triangle. If this line is 1 centimeter, which is the longer distance, from the clown to the dog or from the clown to the rose? The clown.
And the clown to the dog.
Well, Jerry is just looking at it and making an estimation, which is excellent, because at the grade 6 level and also in the CXC CSEC, students are required to make estimation. Therefore, making an estimation is a very good thing. Jerry did not measure it at all. He just looked at it and was able to say that it is the distance from the clown to the dog. But the statement of the problem also gave us the length of a segment or a dash, a line segment or a dash, and it is given to us as 1 centimeter. So which is the longer distance? What do we do with that 1 centimeter? Obviously, the examiners intend that we use that little line that we have there, or little line segment that we have there, as 1 centimeter. So let us go straight ahead and do it. In order to measure any of the line segments, we may take a strip of paper or some other material and cut or tear it to the length of the line that we have in the statement of the problem. So we may use some material to capture the length of that line so that we may use it as our measuring tool to measure the lines. So let us use it. So we are going to measure from the clown to the dog. So we take our strip and we make it the same length as the one that is given to us, and we use it to measure. So we will have about 5.5 of those strips. That's what we will have. So as we see there, the length is not quite 6 centimeters. We may say that it is approximately 5.5 centimeters, because we notice that it is about a half of a strip at the end of it. So what about from the clown to the rose? We may use the same strip, because we have to ensure that it is the same strip or the same length strip, because if we use a different length strip, we may run into trouble, because the measuring would not be consistent. What do we have on this occasion? The distance is not quite 4, but a bit shorter. We may say that it is approximately 4 centimeters. Irrespective of what we do, it will never be as long as 5.5 centimeters. The distance from the clown to the dog is longer. So the strip or the line segment or the dash that was given to us, we use it as a means of measuring the line, and by so doing we were able to show that the distance from the clown to the dog is actually longer than the distance from the clown to the rose. And Jerry made that estimation earlier on, so we have confirmed Jerry's assertion.